Welcome to this CipherVibe Cloud Security Guide. Today we will make OAuth and OIDC Security, step-by-step guide for 2026 practical, prioritized, and connected to how real cloud environments are operated. OAuth is for delegated access, and OpenID Connect adds federated sign-in on top of OAuth. This episode explains how to secure authorization code flows, PKCE, redirect URIs, scopes, consent, client types, token storage, issuer validation, and resource server checks. The purpose is not to memorize a collection of service names. It is to build a mental model you can apply when accounts, teams, workloads, and threats change. We will define the core ideas, walk through a repeatable security workflow, examine mistakes that frequently create exposure, design useful safeguards, and finish with a practical hardening roadmap. Pause when you need to. Write concepts in your own words, record observations, and distinguish what the evidence proves from what you are merely assuming. That habit is more valuable than rushing through another tool demonstration. Start with 4 concepts that provide the vocabulary for OAuth and OIDC security, step-by-step guide for 2026. First, OAuth lets a client obtain limited access to a resource without directly collecting the user password. Second, OpenID Connect adds identity information and ID tokens, but ID tokens are for the client, not general API authorization. Third, public clients such as browsers and mobile apps cannot keep client secrets, which is why PKCE matters. Fourth, redirect URIs are trust boundaries. Exact matching prevents attackers from stealing authorization codes through redirect manipulation. Fifth, scopes and consent should describe least privilege access, not become broad permanent grants. Sixth, resource APIs must validate access tokens for issuer, audience, lifetime, signature or introspection, and authorization policy. Do not study these as isolated definitions. Ask which asset or business service is involved, where the relevant trust boundary sits, which identity performs the action, and what reliable evidence would show that the control worked. Security reasoning is a chain. Source evidence supports an observation. The observation supports a conclusion. The conclusion informs a proportionate decision. The decision has an owner, an expected result, and a way to verify it. When any link is missing, say so. A professional explanation can include uncertainty without becoming vague. For example, a network record may prove that 2 addresses communicated, but it may not prove which human initiated the action or whether the content was malicious. Now turn the mental model into a repeatable workflow. First, inventory every OAuth client, redirect URI, grant type, scope, consent grant, token lifetime, issuer, resource API, and storage location. Second, move interactive user flows to authorization code with PKCE and remove legacy or risky grants where possible. Third, require exact redirect URI matching, narrow scopes, tenant restrictions, issuer validation, and audience validation. Fourth, separate ID token use from access token use so sign-in and API authorization are not confused. Fifth, protect tokens based on client type, secure server storage for confidential clients, and safer browser patterns for public clients. Sixth, test code interception, open redirect, missing PKCE, wrong issuer, wrong audience, excessive scopes, consent abuse, and token replay. Before acting, define the objective, scope, owner, and success condition. Collect the smallest amount of trustworthy evidence needed to understand the situation. Preserve timestamps and sources so another person can follow your reasoning. Priorities should be explainable. Consider exposure, identity and privilege, sensitive data, business importance, exploit conditions, existing safeguards, reversibility, and confidence. A dramatic label should never replace that analysis. The workflow does not end when a command succeeds, a ticket closes, or a dashboard turns green. Verify the new state with fresh evidence. Check for recurrence and for side effects introduced by the change. This disciplined loop, observe, interpret, decide, act, verify, and learn appears in every cybersecurity specialty. Understanding failure modes will protect you from attractive but unreliable shortcuts. First, wildcard or loose redirect URIs can let attackers capture authorization codes or tokens. Second, missing PKCE makes public client authorization codes easier to steal and redeem. Third, overbroad scopes and long-lived consent grants create silent access long after the original need has passed. Fourth, confusing ID tokens with access tokens can put tokens in the wrong audience and weaken API checks. Fifth, storing tokens in browser-accessible locations can expose them to script injection and extension risk. Sixth, accepting tokens from the wrong issuer or tenant can create cross-tenant or malicious provider access. These mistakes often share one cause: confusing an available signal with a complete explanation. A tool can report a finding, a successful action, or a score while important scope, context, ownership, and verification remain missing. Also resist copying commands without understanding their inputs, outputs, permissions, and side effects. Run one controlled change at a time and record what happened. If an exercise does not behave as expected, that is useful evidence. Stop, inspect the environment, revise the hypothesis, and explain the difference. Good security work is not a performance of certainty, it is careful reasoning under imperfect information. Reliable security uses layers because no single control can prevent every failure. First, use authorization code with PKCE for user-facing clients and remove implicit or password-style flows where practical. Second, enforce exact redirect URI matching, registered client metadata, state validation, nonce validation where applicable, and strict issuer checks. Third, use narrow scopes, short access token lifetime, refresh token rotation, consent review, and separate high-risk actions. Fourth, validate access tokens at resource APIs and validate ID tokens only for client sign-in context. Fifth, store tokens according to client type and avoid exposing long-lived credentials to browser script. Sixth, monitor new clients, new redirect URIs, unusual consent grants, failed token validation, refresh spikes, and sensitive API use after new consent. For each important risk, ask 5 questions. What makes the event less likely? What evidence would reveal it? Who can contain it? How will trustworthy operation be restored? Who owns the decision and accepts remaining risk? Least privilege applies to people, applications, devices, automation, data stores, and administrators. Access should be scoped, separated, monitored, reviewed, and removed when it is no longer needed. Every important control needs a test strategy. Include representative normal activity, negative cases, misuse, dependency failure, and rollback. A written policy is not evidence that a technical or operational control works. Finally, preserve the evidence trail from observation through decision, action, and verification. That history supports investigations, audits, lessons learned, and honest measurement. Turn this episode into a practical hardening plan. Start with inventory. Write down every place this authentication pattern appears, who owns it, what data it can reach, where credentials are stored, how it is revoked, and which logs prove normal or suspicious use. Then reduce the biggest exposure first. Remove stale access, shorten lifetimes where possible, narrow scope, protect storage, add recovery or revocation paths, and make sure high-risk workflows require stronger proof. Next, test abuse cases. Do not only test the happy path. Test stolen credentials, expired credentials, replay, reset, or recovery abuse, wrong audience, wrong issuer, missing logs, disabled controls, and emergency revocation. Finally, measure progress with clients without PKCE, wildcard redirect URIs, high-risk consent grants, resource APIs missing audience validation, OAuth client emergency disable time. Each metric needs an owner, a reliable source, a review cadence, and a known limitation. Strong authentication security is a repeatable operating rhythm. Choose the right pattern, reduce credential theft, validate every token or session, protect recovery, centralize evidence, secure machine identity, and rehearse response. For chapter markers and primary links, open the description. For more evidence-based cybersecurity research, visit CipherVibe.com and subscribe to CipherVibe. Copyright 2026 CipherVibe. All rights reserved. This briefing is general education. Validate controls with authorized administrators in your own environment.